Okay, we have our spherical coordinate system, which we often sketch with reference to rectangular coordinates, even though we're not using rectangular coordinates. We have a point at some distance rho, and delta rho, and let's just make this a delta rho, delta theta, delta phi, near the point rho I star, theta j star, brings over a little bit phi k star. Now a small change in rho, let's say starting from this point, would extend us out to distance rho plus delta rho. So let this segment have length delta rho. If our angle phi changes, what's that going to do? Well, that's going to rotate this thing in some direction that's relative to the z direction, so that we would have an image of this same construction here, but at a slightly different angle, phi. So we would have our delta rho here again, but we would also have a dimension here. Now this distance here between this point and this point is what? Well, our angle's changing by delta phi, so the angle in here is delta phi, and our distance is rho sub I star. So let's see, we have a delta phi angle. That would be this small angle in here. And that, as we know from looking at polar coordinates, or as we should be able to discover looking at polar coordinates, recall, this distance here is going to be an arc of a circle of radius rho with central angle delta phi, so that this distance here is going to just be rho delta phi. So this side and this side have length approximately equal to rho sub I star delta phi. Now, same length in here. I don't want to clutter up the figure any more than I already have. Now we ask what the effect would be of a delta theta. We haven't actually located this point. Let's say the point is located here in the x, y, or r theta plane. Then we can construct this line, which lies directly below our line from the origin out to our point in 3 dimensions. That is out to our point rho I star theta j star phi k star. And this line here makes angle theta j star with the positive x-axis. A change in theta then, and let's just say that we have a delta theta that changes our theta in this manner. So we have an angle delta theta in here. as we know, if this distance here is regarded to be r, this results in an arc distance out here along a circle of radius r that's equal to r delta theta. So that's arc distance r delta theta. And that's going to have the effect of rotating our picture in this direction, meaning it's going to rotate this point as if around a circle of radius r. And the same thing is going to happen to the other corner points of this rectangle. They're all going to be rotated in this direction. Giving us something pretty close to a rectangular box. Rectangular because a change in phi will move along an arc that's perpendicular to the radial line that measures our distance from the origin, our rho sub I, and because change in theta moves us in a direction perpendicular to the plane of this rectangle. Now this third dimension of the rectangle, which I haven't labeled yet, is going to be r delta theta. So I'm going to put that up here, r delta theta, and indicate that that's this part of the arc. As we've seen, and as we can see if we look properly at this triangle here, triangle from the origin out to our point down to the x-axis projection of that point, or the xy plane projection of that point, r is nothing but rho times the sine of phi. So r delta theta is in this case equal to rho sub I star sine phi delta theta. Now I should have and intended to draw this picture a little larger, but the point then is that if I have volume increment defined by the change in rho, change in theta, change in phi near this point, rho I star theta j star phi k star, that increment is going to have, well, this line's going to be straight, this line's going to be straight. We'll have an arc corresponding to the delta phi at the distance rho, and an arc corresponding to our delta theta. If delta theta and delta phi are small, these arcs will be very close to straight lines, and their dimensions are going to be delta rho. The dimensions of the rectangle that we approach as these things approach straight lines will be delta rho by rho delta phi by r delta theta, which is rho sine phi delta theta. And rho is, in this case, our sample, the spherical, the distance coordinate of our rho theta phi point, sample point. And this is rho sub I star. This little smudge here is supposed to be kind of an arrow. And we see that the volume now is approximately this dimension by this dimension by this dimension, and that's not a delta rho I star. This is simply a delta rho. Rho I star is the coordinate of the point, delta rho is the rho increment. Okay, so anyhow, delta V is then equal to what? Product of these three dimensions is simply going to have a rho I star squared times, put down the sign phi, and then it's going to be times delta theta, delta phi, delta rho in whatever order. I'm going to choose the order delta rho, delta theta, delta phi. In the limit, delta V becomes our volume increment dV, and everything shrinks down. We lose our subscripts because the points are squeezed down. The sample point is squeezed down to a point, down to a single point. And our volume increment is just going to be rho squared sine phi d rho d theta d phi.